Hi everyone, and welcome to Learn Extra section 8, and in this section we're going to look at interpreting graphs. Now there are certain things you have to bear in mind before you start answering any questions on graphs. You have to firstly try and gather as much information as possible from the graph itself. So here I'm talking about looking at the shape. See and decide what the shape tells you. Also look at any of the titles or any of the information that is given. Look at all the labels of the axes and understand what the variables mean, and also look at the scale. Now just on the point of the scale, that brings us to the next part. Graphs can really be easily manipulated, and oftentimes you'll find in a lot of media reports, and sometimes intentionally and sometimes not intentionally, graphs are put into the media to mislead people who follow these. So don't just look at everything and just believe everything you read, but be cautious and be critical and make sure you understand what you are being shown and see that nothing hidden, there's no hidden information. Okay, we don't want any hidden information. We need to understand fully what the graph is showing us. And so be aware of any hidden information. As I said before, be cautious and be critical of all the information that you are shown. Also, another way that graphs are manipulated is by using the scale. So just on that note, look at your scale. If the scale is too small, then what is really being shown? A bigger scale means more hidden information. So just make sure that you bear those things in mind. Also, another technique that's used to manipulate a graph is 3D techniques, which make things appear larger than they really are. So be aware of any type of these kind of techniques, using a different scale to manipulate a graph, or a 3D technique to sort of get you to believe whatever is put in front of you. All right, so the first example we are going to do is in the context of looking at graphs that are given to you in the media. So here we will look at this question where they say that a local newspaper published this table showing the number of domestic pets in a town. Assume the number of pets in the table are correct. So what they've done is they've put down the type of pets. So you've got this whole lot to choose from: cats, dogs, birds, and so on. And then the number of pets, and then the percentage of pets that are cared for adequately. All right, so this is the table that's published. There's a whole lot of numbers here and the percentages of pets that are cared for adequately. Question 1.1a, why is the total percentage figure, so why is the total percentage figure of 459 obviously incorrect? So let's go to the total and the percentage figure. There we go. So we've got a total of 459% of all pets cared for adequately. Now straight away that should make no sense to you, because remember, all percentages have to add up to 100%. So your total percentage should always be less than or equal to 100%. And therefore it doesn't make sense here to get 459%, so they've just added all of these together. They got 459%. It doesn't make any sense there at all. All right, B asks us to calculate the total percentage of pets cared for adequately and round up to the nearest integer. So in other words, they're asking us to correct the mistake we've just found. We've seen that we've got an answer of 459, which is not possible. So they want to figure out what is the correct answer. Now this is quite a long process that we have to follow. The first thing we need to do is to find out the percentage of pets cared for adequately add all that together and then divide by the total number of pets, and that will tell us what the total percentage of pets cared for is. All right, so let's start. We see that 85% of all cats are cared for adequately. And we know that there are 304 pets, and they told us in the beginning that the number of pets are correct. So this row, all of those numbers are in fact all correct. So we're not being misled there. And we know that 85% of those 304 pets, 304 cats, are being cared for adequately. So if I would like to find out what number of cats are adequately being cared for, all I've got to do is find 85% of 304, so that means times by 304. We can write 85% as 85 over 100 times 304. You guys can do this on your calculator. I've already worked this out, and I get an answer of 258,4. Now, that's the reason they say round up to the nearest integer. Integer, remember, means the nearest whole number. Okay, an integer is not a fraction. And the reason for that is, well, we're talking about pets. We cannot have 258,4 cats. So therefore, it makes sense to round this up to 258. So what we've just found is that 258 of the 304 cats are being cared for adequately. And all we're going to do for the rest of them is exactly the same thing. So we go to the dogs. The dogs that are cared for adequately, we know here we are looking at an amount of 63% of 279. Exactly the same thing. 63 over 100 times 279, and that will give you an answer of 176. And we go through the entire list. So we do that for dogs. The next one we're going to look at is birds. And birds, we are told that 89%, so we write that as 89 over 100, of 195 birds are cared for adequately. We times that together and we get an answer of 174. We move on to fish. And we've got 68% of fish being cared for adequately. So it's 68 over 100 times 195. And that will give us an answer of 133. And then there's reptiles. Reptiles are your things like snakes and lizards and that kind of thing. So reptiles, we have 93% of all reptiles being cared for adequately. So it's 93 over 100 times the number of reptiles, which is 32. And that will give us an answer of 30. And then we have an other column which will take into account all other pets that are not mentioned in the table. There are 65 other pets and 61% are cared for. So we times 61% by 65 and we get an answer of 40. So what we have just determined is the number of all pets that are cared for adequately. So if I would like to work this out as a percentage, all I have to do is to find the total number of pets that are cared for adequately. So that means I have to add all of those numbers together. So 176 plus 174 plus 258 and so on and so on and so on. So we're basically just going through these, adding 258, 176, 174, 133, 30, 40, and all of those numbers, and then we're going to divide that by the total number of pets, which is 1070, and times that by 100. So in other words, I'm just finding a percentage. So I take all of these numbers, add them up, divide by 1070, and times by 100, and this will give me a percentage of 79%. So this figure, 459, was very, very wrong, because it is in fact only 79% of all pets that are cared for adequately. So you can see that this is very, very misleading. Okay, guys, let's continue to the next part of this question. We are told that a newspaper report accompanying the table that we have just looked at makes a number of claims. They then want us to state whether we agree or disagree with each of them, and then give reasons for your answers. All right, so obviously we're going to have to work this out in order to be able to disagree or agree. They say only 63 of the dogs are cared for adequately. So let's go back to our table. Only 63 of all the dogs. No, only 63% of all the dogs are cared for adequately. This is not the number of dogs. This is the percentage of dogs that are cared for adequately. If I would like to find out the number of dogs that are cared for adequately, I need to take the 63% and times that by the number of dogs, which is 279, and that would give me an answer of 176. So 176 dogs are cared for, and therefore we have to disagree with what they said, because they said 63 of the dogs were cared for. All right, the next one. They say just over a third. Now a third is 1 over 3, which is roughly equivalent to 33.3%. They say just over a third of the domestic pets are cats. So let's go and look at the number of cats. We know that there are 304 cats, and altogether there are 1,070 pets. So if I would like to find out what percentage of this town the cats make up, all I do is take the number of cats divided by the total number of pets and times by 100. So I want to either agree or disagree after making my calculation. You do this bit on your calculator and you get an answer of 28.4%. 28.4% is definitely not equal to 33.3%. So once again, we would disagree and obviously show your working in order to back up your answer. So let's do the C part of this question now, where they ask us, or where they say 611 pets are being neglected. So let's determine if 611 pets are in fact being neglected. Remember, in the previous question, we had to work out the number of pets that were cared for in order to work out the percentage that were cared for. And that would have given us 841 pets that were cared for, and that we got by adding all of those numbers at the bottom. So all of that's 258, 176, 174, and so on and so on. That would give us an answer of 841. So in order to determine if 611 pets are being neglected, all we have to do, since 841 are being cared for, we have to subtract that amount from the total number of pets, which is 1,070, and 1,070 minus 841, which was worked out in 1.1, this will give us an answer of 229. So therefore, no, not 611 pets are being neglected. It's actually 229 pets. So therefore, once again, we would disagree. All right, guys, let's do the last part of example 1.2. They say that it is interesting to note that more reptiles than cats or dogs are being cared for adequately. So they say basically that more reptiles than cats or dogs are being cared for adequately. Do we agree or do we disagree? Let's go back to our table. In the table, we see that there are 32 reptiles, 279 dogs, and 304 cats. Now, although there's a much higher percentage of reptiles being cared for, so 93% of all 32 reptiles are being cared for adequately, the number 32 is much smaller than the number of dogs and the number of cats. So although these are smaller percentages, when you work this percentage out of bigger numbers, you are in fact going to get a bigger answer than we are going to get if we work out 93% of 32. So we have already in fact worked this out. Let's just go down to our table here. For the cats, we saw there were 258 cats that were cared for and 176 dogs. But when you look at the reptiles, 30 are being cared for adequately. And that's because we are finding 93% of a smaller number. So obviously 93%, so even though it's quite a large percentage, we're finding 93% of a smaller number than the cats and the dogs. This would mean that in fact, no, it is not more reptiles that are being cared for adequately. So once again, we would disagree. And the reason here is that although the percentage is higher, since the number of reptiles is smaller than the number of cats and dogs, it implies that it would give us a smaller answer in the end. Okay, now that we are done with example 1.1, which is quite a long example, and it's just an example of the way certain things can be represented and mislead you, let's move on to example 2, which is also another way to interpret graphs. We are told in example 2 that 10 young children were monitored and over several weeks to measure the number of hours they spend watching violent TV shows. And then we looked at the number of acts of violence towards their playmates. So in other words, if they watched a violent show on TV, were they then violent towards the people they were playing with? We are told that the charts will illustrate the results. And you can see it's labeled hours viewing TV violence per week. That's on the x-axis, so that you can identify as your independent variable. And then the number of violent acts. So straight away, what this graph is suggesting is that the number of violent acts that these kids commit is directly influenced by the number of hours that they spend watching TV. So let's have a look if that is in fact the case. And there's a whole lot of points scattered throughout that graph. So here they say, identify the point that represents the child who watches, and in the first case, we're looking at the least hours of violent TV shows. So they watch the smallest amounts of violent TV in the week. So your hours of violent TV, that's measured on your x-axis. So if I'm looking for the least hours, I want the one that's closest to naught. Okay, because at that point they're watching 0 hours of violent TV. And we see that the point that's closest to naught, in fact, it's naught on the x-axis, so they spend no time watching violent TV, is the point A. So the least hours of violent TV shows we identify at point A. The next part would like the greatest number of hours of violent TV. So there, once again, we are talking about the x-axis, the one that would be the furthest away from 0. So I see that that will be at the point I, because that child there, child I, watches the most amounts of violent TV compared to all the other points. So all the other letters, that's the one. I, that's the one that's furthest away from 0. Okay, part C would like to know which points shows us the greatest number of hours of violent TV per week and is the most violent to their playmates. So at the same time, they're watching the most amount of violent TV. So that's, we've just identified as point I, and they're the most violent towards their playmates. So while I and H are both equally violent towards their playmates, it is this point I that watches the most amount of violent TV as well. So therefore the answer to the C part of this would once again be I. Part D would like to know, what do child I and H have in common? We in fact don't have to go back up there because I've already answered it. They both were at exactly the same point on the y-axis, so they both commit the same amount of violent acts towards their playmates. So they both commit the same amount of violent acts, and that's exactly what they have in common. So let's just go up here and show you once again. H and I, they're both hitting the same point on the y-axis, so therefore they are both equally violent towards their playmates. All right, let's move on to the next one. They ask us to mark the point J on our graph, which represents the child who watched the same hours of violent TV. So that gives us an x-axis as a point of reference. It's got to be the same number of hours of violent TV as child G, but displays 7 acts of violence. So we go back to our graph. Let's identify this amount of hours. So child G is there just above 8. So this child that we are talking about at point J would have to watch the same amount of hours. So it needs to be in exactly the same horizontal distance from the point north. So it would be in the same here horizontal distance, but they commit less acts of violence. So it's going to be slightly below the point G, and we call that the point J because they display less violent acts. We are told to mark it at the point 7. So we saw that it's at exactly the same point as G, so it's just below it because there are less acts of violence. So this one we put on the graph. All right. And then F would like us to write a sentence to describe the relationship between the hours of viewing violence on TV and violent behavior. So let's go back to the graph and let's look at what's happening. And obviously we would write this down in words, but what you can see is that as the number of hours of violent TV viewing increases, so as we increase on the x-axis, we see that the same thing happens on the y-axis. We also increase on the y-axis. So what we ultimately find at the end of this question is that as the kids watched more and more violent TV, they became more and more violent towards their playmates. We're now going to look at a specific type of graphs that we are going to interpret. This type of graphs are called speed and distance and time graphs. So what we have here is we have time represented on the x-axis, and we have our distance on the y-axis. Now your time can be in anything, generally minutes, hours or seconds or whatever the case is, and your distance can be meters, kilometers, and so on and so on. So these are quite typical graphs that you will come across quite a lot when you have to interpret graphs. So let's look at each of these sections, and I will just explain to you what's happening over each of these sections on the graph. In this first part, if we go, it's sort of going at an incline, so we've got an increase in distance from naught to that point. So if we call that A shows an increase in distance. So the person started there at time 0 with distance 0, and by that point they're much further away from where they started. So that will show us an increase in distance, and obviously a certain amount of time would have elapsed. Now if we look at the next section, I can call that bit B. What we see there is an elapsing in time. So time has passed, but the distance hasn't. So the distance is exactly the same as where we ended there at point A, but the time has passed. So time has passed, distance is the same, therefore this point will represent a resting period. Because the distance hasn't changed, this will just be where the person is resting. Once again, you see this incline or this increase. This would imply an increase in distance that we can call C. And then at the end of C, you see that the line starts sloping to the left, so it has a negative gradient, and that would imply a decrease in distance. So the person is going back the way they came. So it's decreasing distance, but what it really implies is that they're actually going back. So although they're still walking and there is some distance involved, they're going backwards. They're going back to where they started. All right, so those are just the different types of portions, different types of points on this graph. And so those are the little things you need to remember when you interpret distance time graphs. All right, so let's go through them again. The first part represents an increase in distance. When nothing is happening with your distance, that's a resting period. We then have an increase in distance, and then we have a period where we are, in fact, not decreasing distance, but rather we are going back. We're going back the way we came. All right, so bearing that in mind, let's answer the questions that are posed to us in example 3, where we are given this this distance and time graph. We are told that Zena walks for 10 seconds. So there's our time. Our total time is 10 seconds. While Grant records her distance from where she started in 1 second intervals. So it's going to go up. Our time is going to go up in 1 second intervals. From the information that they record, they then draw the following graph. So before we actually look at the questions, because there will be questions on this graph, let's identify the different pieces to this graph. We see that the x-axis represents our time in seconds, so that's how long she's taking to complete her journey. And then the y-axis tells us how far she has gone from the start to that point in time. So the first little section from 0 to about 4 seconds, we see that her distance at that point is about 4 and this is in meters, so it's about 4 meters. And then from the 4th second to about the 8th second, we see that that's just a horizontal portion, which means that no movement happened there. So in other words, it was a time when she rested. And then she started walking again from the 8th second to the 10th second. All right, so they say with the use of the graph, answer the questions. Firstly, what quantity is plotted on the vertical axis? Remember, vertical is another way to say the y-axis. So on the vertical axis, we had total distance being plotted, and that was in meters. All right, the next part, how far does Zena walk in 5 seconds? Now, in order to answer that, we've got to look at the graph and look at what happens along the 5th second. So the 5th second is between time 4 and 6. I would say it's about halfway, somewhere there. All right, so what's happened in the 5th second? We saw, well, from 0 to about the 4th second, she walked a distance of 4 meters. So she walked 4 meters there. And in the 5th second, she actually isn't going anywhere, because here we just have time passing but no distance. So by the 5th second, she still only walked 4 meters, because at this point it's flat. It means she's resting. So therefore in the 5th second, she has only walked 4 meters. Part C. What was Zena doing during the interval from 4 to 7 seconds? We don't even have to look at it. I've repeated it time and time again now. 4 to 7 seconds, nothing was happening. Her distance wasn't changing, so she was resting. All right. And then finally, part D. If speed is equal to distance over time, determine Zena's speed for the entire trip. So average speed is equal to distance over time. Determine her speed for the entire trip. So 2 things we need in order to work this out. We obviously need her total distance and we need her total time. We were told right at the beginning of the question that Grant was recording this for 10 seconds. So her total time is 10 seconds. And the total distance, we have to actually go to the graph and work that out. So all we've got to do is let's just go to the graph and work out what the total distance is. We know that at the beginning, she had a distance of 4 meters, so we've got to take that into account, which is that little piece there. That's where her distance increased. Nothing happened with the distance in the portion from 4th to 7th second, so it's really from the 7th second onwards that we need to be interested in. That's where she increased her distance again. So all we've got to do to find out the total distance is add these two little pieces together, the 4 meter piece and then this from the 7th second onwards. So in order to do that, I go to this portion. I see that she stopped resting at the 7th second, and from that point she made she sort of walked this distance. I need to find out what that distance is. So all I've got to do is go across from this point and see where it hits the y-axis, and that's roughly about 17,5 on the y-axis. So that's the distance she's done, but it's not 17,5 from the start. It's 17,5 from this point where she stopped resting. So she didn't go back and start again. It's from this point where she's already walked for 4 meters. So if I would like to know what that distance is, I need to say 17,5 minus 4 meters, which will give me 13,5 meters. So in this last portion, she walked for 13,5 meters, and at the beginning, she had a distance of 4 meters. So altogether, what we would have to do to work out her total distance is add the 4 to the 13,5 meters, and that will be 17,5 meters. Now that we have her total time and her total distance, we can work out her speed by saying speed is distance over time. So it's 17,5 meters and 10 seconds. And that will give us an answer of 1,75 meters per second. So she was going at a speed of 1,75 meters per second. Guys, we're going to continue looking at examples of speed, distance, and time, and this will be example 4. In example 4, we are told that John entered a sponsored walk to raise funds for an animal shelter. The graph shows his progress during the walk, which we are told that he does finish. They ask us to use the graph to answer the questions, okay? So before we actually start answering the questions, let's look at the graph. We see that his time is measured in minutes on the x-axis, and then his total distance is measured in kilometers on the y-axis. So we've got time in minutes and distance in kilometers. They've also marked off a point A on the graph, and we see that it is in fact a straight line, so that's the total distance that he has covered. He hasn't rested at any point, so it's an increasing graph. All right, so let's answer the questions. They want to know what was the total distance of the walk. So in order to find the total distance of the walk, we basically just need to see how far along this graph goes. We see that he started at 0 and he stops at that point at 200 minutes. So if I want to see what the total distance is, all I need to do is just go across from his time, and that's about 20 minutes. So, sorry, not 20 minutes, 20 kilometers. So the total walk took him a distance, or he walked a distance of 20 kilometers. We then would like to know in 4.2, how many minutes did John take to reach point A? So in order to determine that, we go to point A on the graph. Okay, that's a distance of about 4 kilometers on the y-axis. To find out the time, we just drop down onto the x-axis, and we see that the time taken to reach point A is 40 minutes. So therefore 40 minutes to reach point A. They would then like to know how many minutes it took him to cover 10 kilometers. So again, we're looking at minutes, so that means we're interested in the x-axis. and all we've got to do is go to 10 kilometers on the y-axis, go across, and where that hits the actual line that shows his distance, we drop down and we see that that will take us to 100 minutes. So if we just drop down and read from 10 kilometers, we see that it will take him 100 minutes to reach 10 kilometers or to cover 10 kilometers. So as you can see, these are very basic questions, but you need to have a good understanding of what your graph is showing you in order to know whether you should be looking at the x-axis or the y-axis. How long does it take him to cover 15 kilometers? So once again, exactly the same thing. We go across to 15, which is somewhere between 14 and 16 on the y-axis, and we then drop a line where 15 would hit his line that shows how far he's walked. So we go to 15, we go across, and where that line hits the line, the black line, which shows how far he's walked, we drop down and read off from the x-axis the value, and that value is roughly about 150 minutes on the x-axis. All right, then in 4.3, they would like us to calculate the time in hours he took to complete the walk. Well, what we've just seen from the graph is that this entire walk, remember, was 20 k's from point A. We want to know how long it took him to walk those 20 k's, and it in fact took him 200 minutes. So that means the entire walk was 200 minutes. If I would like to convert minutes to hours, all I've got to do is divide by 60. Because remember, there are 60 minutes in 1 hour. So 200 minutes divided by 60 minutes will tell me how many hours this translates to. And we can cancel the 0. So we get 20 over 6, which would give us an answer of 3,3 hours. So rounded off to the first decimal place, we get an answer of 3,3 hours. The next part would like us to determine John's average walking speed in kilometers per hour. So we've just worked out that his time to complete the whole walk is 3,3 hours. And we know that his distance, so the total walk, was in fact 20 kilometers. And they would like us to work out his speed. Remember that speed is equal to distance over time. And they want it in the units kilometers per hour. So all I've got to do is take my 20 kilometers divided by 3,3 hours. And if you do that on your calculator, you would get an answer of 6,1 kilometers per hour. So that's John's average speed for the race, for the walk, sorry. Now, in the last part, they ask us to work out the winner's time if John completed the walk in 200 minutes and the winner completed the walk in 78% of John's time. So if I would like to work out the winner's time, because I know it's a percentage of John's time, all I've got to do to find a percentage is take 78 divided by 100 and then times it by the number of minutes. So we can do that on our calculator if you like, and if you do that, 78 over 100 times 200 would give you an answer of 156, and here we are talking about minutes. Since John completed the walk in 200 minutes, the winner would have completed it in 156 minutes. And guys, that's the last time, distance, and speed question that we will look at when it comes to interpreting graphs. It just takes a matter of practice and understanding what each little portion of those distance time graphs are telling you, and you'll be perfect at that section. Now we're going to look at the last example in this section on interpreting graphs and tables. In example 5, we are going to interpret a table that is given to us. They say this nutritional information is printed on a 500-gram packet of crisp bread. So this is often, if you look at the back of any type of packet, they'll always have some sort of nutritional information. So it is something that you do often see in reality. So at the back of the pack, it says nutritional information. It then has typical values. So you have your values per 100 gram and then per individual biscuit. They then look at things like the energy, which is the kilojoules. They look at protein, carbohydrates, and fat, and all of that. They say the figures per 100 gram, so that means they're talking about this column, those figures, as well as the typical mass of one biscuit are correct. So all that we know for a fact that's correct in this table is this second column and the mass per biscuit. So those are the only two things that we know for a fact. They then say, how can you tell at a glance that the figure per biscuit for protein is incorrect? So let's go through and have a look at the figures per biscuit. Okay, so per biscuit, we know that each biscuit weighs 6,34 grams. And then we've got the energy content, protein content, carbohydrates, and total fat per biscuit. And straight away, you can see that there's this glaring mistake. It doesn't actually make any sense, because if we look at this, we see that we have a value of 8,32, which is in fact greater than the mass of the biscuit. So how is it possible to have more protein than the actual mass of the biscuit? Doesn't make any sense. So at a glance, we can tell that the figure is incorrect, since the mass of protein is greater than the mass, or you can write this out obviously as is greater than, I'm just putting it in symbol form, is greater than the mass of the individual biscuit. Alright, so that's a glaring and obvious mistake. Now, part B would like us to calculate the correct value. So remember, what we know for a fact is that there's 13,12 grams of protein per 100 gram. So if I would like to work out what that translates to per biscuit, all I have to do is take 13.12 and times that by the mass of each individual biscuit, and then we're going to divide it by the number of grams that we are that we were given, which is 100 grams. So we take 13,12 times that by 6,34 over 100. So in other words, we get it into the correct proportion. And then we can put that into our calculator. So let's call up a calculator. So we're going to have 13.12 times 6.34 divided by 100, and that will give us an answer of 0.83 grams. Okay, if we round that off to 2 decimal places, that will be 0.83 grams, which makes much more sense for this to be in the correct proportion that it is for the packet. All right, part C. They say there is one more mistake in the table in the per biscuit column. They would like us to find it and correct it. Now, what you would have to do in that case is you would have to work out each of these values, doing exactly what I've just shown you. Take this amount and times it by 6,34 over 100 to get it in the right proportion. And you will then go through each of the figures and check that each of them are in fact correct. Alright, so that one we've already corrected, the protein one. Now, if you go through each of these, you will see that the figure that's not correct is the carbohydrates figure. So that means this is the one that we have identified, and this is the one that we need to correct. Alright, but that's just a process of trial and error and going through it one by one. So in order to correct the mistake, there was 69.28 grams of carbohydrates per 100 grams packet. And if I would like to convert that into one biscuit, I need to then times by 6,34, divide by 100. Once again, we can do that on the calculator. So it's 69.28 times 6.34 divided by 100. And that gives us an answer of 4,39. So it's slightly higher than the 4,34 that was originally written down in the table. Finally, about how many biscuits does a 500-gram packet contain? So 500 grams, we know that each biscuit weighs 6,34 grams, and 500 grams is a really big packet, all right? So if I would like to know how many biscuits this big packet contains, all I've got to do is take the total weight, which is 500 grams, divided by the weight of each individual biscuit, and that will then tell me how many biscuits I can put into a 500-gram packet. So once again on our calculator, 500 divided by 6.34, that will give us an answer of 78,86. So we've got 78,86. Now because we're talking about a number of things, a number of biscuits, we obviously can't put in 0.86 of a biscuit into a packet. So that would mean that there's approximately 78 biscuits in a 500-gram packet. And guys, that's the last example that we are going to look at on interpreting graphs and interpreting tables. Make sure that you practice this, and remember to always be cautious and be critical when you examine and interpret any graph or table. Sean is traveling a distance of 600 kilometers. The time taken to complete the journey depends on the speed he travels. 1A. Complete the table and round off to 1 decimal place. Part B. Draw a graph showing the relationship between speed and time. And part C. Describe the relationship this graph illustrates. Let's do the first part. Sean, we are told, is traveling a distance of 600 kilometers, so that is fixed. The time taken to complete the journey depends on the speed. Obviously, the faster he's going to go, the quicker he's going to get there. But let's see if that relationship follows through with our answers. They asked us to complete the table and then round off to one decimal place. Let's look at the first one. They give us different speeds, so we've got 60, 70, 80, 90, 100 and 120, all in kilometers per hour. And they tell us to work out the time in hours. So this one is a little bit tricky because what we need to remember is that speed is given by distance over time. And the reason it's a little bit tricky is because you need to realize that your distance was already given to you in the beginning as 600 kilometers. So that's the same distance he is going to be covering at all these different speeds. Okay, so his distance is 600 kilometers. The speed is given to us, all the different values. So what we actually need to work out is the time. So what you would have to do is manipulate your formula, and you will get, by changing the subject of the formula, you will get that time is equal to distance over speed. Now, in most cases, these formulae are given to you in your exam when you're expected to use it. Sometimes it's not, so it's always a good idea to know it, but they generally are given to you. So your time will be equal to your distance over your speed. So I'll do some of them for you. In the first case, our distance is 600 kilometers and our speed is 60 kilometers per hour. Therefore, 600 divided by 60, easy enough, will give me 10 hours. So it would take 10 hours to cover a distance of 600 kilometers at a speed of 60 kilometers per hour. Now, if you go through the table in a similar manner, so if I would like to work out his time when he's traveling at 70 kilometers, I would take 600 divided by 70, and for 80 the same thing, 90 the same thing, and so on and so on. You will then be able to fill in this table by using your calculator. You will get 8,6 hours when he's traveling at 70 kilometers per hour, 7,5 hours when he's traveling at 80, 6,7 hours at a speed of 90, 6 hours at a speed of 100, and 5 hours at a speed of 120. So without even looking at any of the other questions, we can immediately see that obviously as he is increasing his speed, it's taking a shorter time, so a shorter amount of time to complete the same distance, which is the general relationship between speed and time, but we will get to that. They then ask us to draw a graph showing the relationship between speed and time. Now, all I've done on this graph, we've got speed on the x-axis and time on the y-axis. I've literally just plotted the points from the table that we've worked out, and what you can see is that we have this hyperbolic type shape. Remember, we said right in the beginning of sketching graphs, which was in session 7, that when you have an inversely proportional relationship, you will get a hyperbola type shape since they are inversely proportional. You can in fact join the dots because both speed and time are continuous. So if we do join the dots up, our shape becomes quite apparent. So definitely an inversely proportional relationship, which in fact helps us to answer the last part, which says, describe the relationship the graph illustrates. It is illustrating an inverse relationship. Since what we've seen is that as your speed increased, the time taken to complete the same trip decreased. So this was in fact an inversely proportional relationship. Guys, we're now going to move on to the last exercise, which is exercise 2. Exercise 2. HIV and AIDS is recognized worldwide as a threat to children and their families. The graph below illustrates how the number of HIV and AIDS orphans as a percentage of all children in Lesotho has changed from 1990 to 2010. Use the graph to answer the questions. Question 2a. In which year was the proportion of HIV and AIDS orphans the lowest? B. In which year will almost 1/5 of children have become orphans as a result of HIV and AIDS? C. What percentage of children would be left orphaned by HIV/AIDS in 2010? And in which 5-year period was the increase in the proportion of HIV and AIDS orphans the greatest? So we are told that HIV is recognized worldwide as a threat, and they then give us a graph which illustrates the number of orphans in Lesotho, and this has changed from 1990 to 2010. This type of graph is called a line graph. It shows you how quantities change over time, and your axis must always have your units. So on the y-axis we have percentages, and on the year, obviously that's in years. All right, so this is a line graph just showing you how things change from one point to another. We see that on the years, which is on the x-axis, we are going up in 5-year periods, and we're going up in percentages of 5 on the y-axis. The first part would like us to know, would like us to tell them in which year was the proportion, that's the same as saying percentage, of HIV and AIDS orphans the lowest. So all we've got to do is go to our graph and look for the lowest point. And we see that the lowest point of this graph, remember that's your number, so that's measuring the percentage on the y-axis, and the lowest percentage was in fact in the year 1995. So therefore the first answer would be 1995. Then part B, in which year will almost 1/5, you first have to realize that you need to change that to a percentage form in order to understand what they're asking you in percentage terms. 1/5 is the same as 20%. So they want to know in which year will almost 20% of children have become orphans. So we go back to our graph here. And 20%, all we're going to do, 20% is on the y-axis. We are then going to draw a line, follow it across, and see when that hits the line graph, and that will then tell us in what year that happened. So we go across, and we see that just by reading it off from the graph, if we drop down onto the x-axis, that was in the year 2005. So that's the answer to part B. Part C, what percentage of children will be left orphaned by AIDS in 2010? So here we need to start, because they've given us the year, we start in 2010 and we go across and read it off. So once again, we make use of a ruler, or in my case a straight line. I'm going to go across, and I'm going to then go across on my axis and read it off. And what you will see is that if we follow this onto the y-axis, it's very close. It's somewhere between 20 and 25%. So we'll say it's roughly about 23%. So plus minus 23%. And then finally, in which 5-year period was the increase in the proportion of HIV and AIDS orphans the greatest? So what we need to do is, on the graph, we need to look for the biggest change or the biggest gap. And we see that the biggest gap would actually be from the years 2000 to 2005. So what you will see is that's the biggest increase that you will have in any of the 5-year periods, and therefore it is from 2000 to 2005 that we have the highest increase in the number of HIV and AIDS orphans.